Well, good evening, everybody. Wow, a lot of people interested in science. Very cool, very cool. And unlike other parts of the country, Tellus is open. We don't have a shutdown. All right. A couple of things. For those of you just coming in, we're going to try to bring in some extra chairs. There's a few stray seats around. David, if you could maybe point to a few, we'll try to accommodate as many of you as possible. So I'm Jose Santamaria. I'm the museum director here. I'd like to welcome you. A couple of things, a couple of housekeeping things. If you've been here before, you know the drill. Get these guys off or on buzz. No flash photography. We do not want a blinded and annoyed speaker. If you must do something like this, please keep the screens down because then you're really affecting your neighbors. And we are broadcasting this out into the Great Hall. So if you get some fidgety small ones, feel free to take them out because you won't miss anything. The lecture will be broadcast out there. A couple of other announcements. The weather is not looking too favorable right now for the observatory, but I'll give you an update when the lecture ends to see if the skies cooperate. But the museum is open. The museum is open till 9 o'clock tonight. And there's two exhibits you may want to check out in case you haven't seen them because they closed this weekend. Our Gem and Mineral Treasures of the Southeast in the vault, which is in the Mineral Gallery, and Brain Teasers, a really fun interactive in the Discovery Garden of my big backyard. Okay, did I miss anything, David? All right, so very exciting time for space exploration. We have inside land on Mars to conduct geological studies. We have probes going to the sun. One landed in the far side of the moon. But really, one of the most exciting missions right now is surveying objects way beyond Pluto, and that's what we're going to be talking about tonight. So to introduce our speaker, I'd like to bring our astronomer, David Dundee.
Thank you so much for being here for our special event. This is quite a coup, and I'm really excited to have Mark here. I've known Mark for the past 3 years. We got him as a keynote speaker for a planetarium conference here at Tellus 3 years ago when the New Horizons spacecraft just flew by Pluto. And who knew that 3 years later we'd have him back for yet another flyby. And Mark is a very cool guy, as you're about to find out. Got a great sense of humor. He loves rock climbing. He loves diving for megalodon shark teeth. He loves astrophotography and caving. Mark got his degrees in astronomy and physics from Ohio State University, and he joined the Hubble Space Telescope team early on before the launch of Hubble. And then after that, he worked on the far ultraviolet spectroscopic explorer. And then he worked on the Messenger spacecraft, the one that went to Mercury. He was also on the mission team for the early New Horizons spacecraft with a flyby of Pluto. And then he took a little break from that and worked on the Mars Reconnaissance Orbiter and came back to the New Horizons spacecraft. And that's where we're here tonight. Back on January 1st, a whole 3 days ago, the New Horizons spacecraft was 1 billion miles further out from Pluto and passed, for the very first time in human history, close pass of a Kuiper Belt object. And to put this in perspective this evening, folks, if you go back in time before the birth of the planets, before there were planets, and just kind of this large nebula, a big gas cloud, the outer regions of the gas cloud still exist today, about 1/3 of a light year out from the sun, and this is what's called the Oort cloud, a cloud of debris that we think comets come from. Well, after that period, a few billion years later, it collapses down into a disk. And now imagine a whole disk of material now rotating around the center of what's becoming the sun of icy material. Now, all that icy material disappears thanks to the sun and the planets, except for the very outer part of the solar system, about 1 billion miles further out from Pluto. a whole region of particles that even with a Hubble Space Telescope look like very faint smudges. For the first time, folks, you're going to see images tonight of a Kuiper Belt object that has never, ever been seen before. We're very, very excited. I'm very excited to present tonight my friend Mark. Come on up, Mark Kochte. Thank you,
Thank you, David. Get out of the way. Good evening, everyone. For those who are standing, there's still like one seat there, there's a seat there. But wow, there's a lot of people here. So we're going to do a thing. I'm going to take a photo of you guys. So I can show this to my mission operations manager. Said, look, few people came out to see this. So just a quick background about me, in addition to what David just threw at you. My role on the mission is I'm a mission planner. I coordinate with all the subsystems on the spacecraft, the instrument teams, the guidance and control, the autonomy, the power teams, navigation teams, to get their input to put together the schedule that the spacecraft has to follow over a given period of time. This period of time, what we call a command load, is about 1 week or 2 weeks or 3 weeks, depending on the activity going on the spacecraft. There's a small team of us that do this, and we rotate over these command loads. And it takes us about 5 weeks or so to build these loads. So we get the first inputs in from the teams, we vet them, see what their conflicts are, get things cleaned up, have deconflict conflict problems. And in that 5-week period, we should have a schedule that's ready to be uplinked to the spacecraft. And the spacecraft is light hours away, and radio signals travel at the speed of light. So sending a signal to, we can't joystick the spacecraft. We have to send these command loads up so it knows what to do for a week or 2 or 3 period. And in the meantime, we're working on the next batches of these schedules. So, nutshell, that's what I do on my day job. For fun, I do talk for you guys. So, I work at the Johns Hopkins University Applied Physics Laboratory. It's a private organization. It's not a government furloughed organization. So we're still operating, we're still running. And even if we were furloughed, I could still come and give talks. They're not paying me to do this. Anyway, what I'd like to do tonight is, I'm going to be throwing a lot of information at you. So I'm going to hope if we could try and save the questions to the end, especially since I got this blinding light here and I can't see most people in this area if you raise your hand. Try and save it to the end if you can. If you really need a burning answer to something, I'll try and answer it at that moment. But what I want to do is give you a quick overview of the solar system as a whole, so we're all on the same page, and then give you a brief tour of the Pluto system that we visited 3 years ago, just to catch you up on things, remind you of what we've got to see, what the things we've discovered there, and then hit Ultima Thule, the object we just flew past 3 days ago. So without further ado, our solar system is a very, very complex environment. We have these rocky worlds, we have these gas giants, and we have a lot of other things in there, comets, asteroids, meteoroids, Kuiper Belt object things. So over time, the understanding of our solar system has evolved, and we now categorize the solar system into 3 zones. Zone 1 is the inner zone. It's from the asteroid belt inward to the sun. That's where all the rocky worlds are, Mercury, Venus, Earth, and Mars. Zone 2 is basically the middle zone, because if you have 3 zones, you have to have a middle. And it has gas giants. It goes from the asteroid belt outward to the inner part of the Kuiper Belt. And that contains Jupiter, Saturn, Uranus, and Neptune. Zone 3 is the least understood zone right now. And in fact, up until a couple decades ago, we didn't even know it existed. We theorized it was there, but no one knew it really existed, that there was actually things out there for us to see. It's a donut-shaped area. It extends from the outer orbit of Neptune out about 50 astronomical units. So an astronomical unit is the mean distance from the Earth to the Sun. That's 1 AU. So from 30 times to 50 times further out from the Sun is the Kuiper Belt, as you can see here. And for those of you who are watching live stream, I don't think you're going to see the laser pointer, so you have to look at the lower right image to see the Kuiper Belt. It's a donut-shaped thing, as I mentioned, and it's full of objects that are meters across, to tens of meters across, to hundreds of meters across, upwards to kilometers or so across. Pluto is a member of the Kuiper Belt. So Pluto was discovered back in 1930 by Clyde Tombaugh. He was charged by Percival Lowell, a famous astronomer at the time, to look for planet 10, or planet X, not 10, planet X. And so he started looking at these photographic plates, giant glass plates that astronomers would take images of the sky on, and he would take a plate from one time period and a plate from like 5-6 months later, same part of the sky, and put them in what they call a blink machine. So it'd be side by side, and there would be one side would be illuminated. He'd be looking at eyepiece where it would be directed, and then he would turn that light off. At the same time, a light on the other side would illuminate, and the stars would not move. So anything that was not moving in that field of view was a star, and anything that moved was something in our solar system. And he found all kinds of things. He found galaxies that no one had seen before. He found star clusters. He found variable stars. And he found this object that moved. And he thought, that's weird. He brought to his boss. They looked at it, and they calculated the orbit out. And they saw that it had this long elliptical orbit, unlike the classical planets that we knew before. But it was the only thing out there like it. So they called it a planet. This is on the lower right here. You can see the time scale of Pluto as it went around its orbit and different things in our own history that occurred when. On the left here, you can see how inclined Pluto's orbit is relative to the disk. Relative to the disk of the classical planet. Its orbit's about not quite 250 years, 248 years. Its last closest approach was in 1989. It's heading out further from the sun in its orbit. So it's entering now late summer, early fall in its season. And if you do the math, 248 years divided by 4, the seasons are rather long. Now, when it was discovered, they didn't have a name for it. They just had, look, planet, there's something out there. Cool. But what do we call it? Well, they didn't have a formal way of naming anything, but news of this discovery spread around the world amongst the astronomy community and then the non-astronomy. And this young woman here, Venetia Burney, she was 11 years old at the time. She was having breakfast when her dad was reading her about, in a newspaper, about this discovery the Americans made of this new planet way out in the outer fringes of the known solar system. She was very versed in the classical mythology, and that's what it was called. And he said they don't have a name for it. He said, well, what about Pluto? Which follows the pantheon of all the gods that we've named all the planets after. Pluto is the god of the underworld, god of the invisible. The object, Pluto, is extremely faint. It's barely visible. And it turned out that people had been actually imaging Pluto with telescopes for years before Clyde recognized that he saw it in the astronomical plate, but no one knew. So her dad sent back a telegram that said, my daughter suggested name it Pluto. Clyde Tombaugh said, hey, that's cool, not just because it follows the pantheon, but because the initials TL are his boss, Percival Lowell. So for decades, we had just this one oddball planet. When I was a kid, I remember when I was getting into astronomy, I started in 8th grade. I was just like, bam, astronomy, that's what I want to do. And I studied the planets, and I thought, oh, Pluto, that's weird. It just has this weird orbit. It has this weird elongation to it. But we knew nothing else out there, so we call it a planet, along with all the other planets. Over time, especially in the last 15, 20 years, we've been discovering more and more bodies out beyond Pluto. Many of them are small, hundreds of meters across, but some of them were large enough that they formed roundish bodies. They had mass. So we discovered Haumea, we discovered Makemake, discovered Sedna, Quarwar. And then someone discovered Eris, not Eros, Eris. Eris, they had measured at that time, was just a little bit larger than Pluto. And people said, no. Pluto's bigger. And then you had Eris people, no. Eris is bigger. And there's this little controversy going on until they could measure it. And they ultimately discovered that Eris is just a few kilometers shy of Pluto size. But it's as large as Pluto, essentially, which means at this point, if you count all the other large bodies out there as classical planets, we now have 13 or 14 planets. I don't personally have a problem with that. I mean, there's 50 states you have to memorize. You can memorize 13 planets. But some people had issues with this, and there was all this controversy. And ultimately, back in 2006, there was a vote done in the IAU, the International Astronomical Union. I'm not going to go into the details of it. We can take that offline if you want. And it was decided that Pluto was going to be classified as a dwarf planet. A lot of people got emotionally charged about this. But if you pause for just a second, this is how science works. You look at something. If you only have one of something, you can't categorize it as anything until you have more items that resemble it. Haumea, Makemake, Eris, Sedna, Quarwar, they resemble Pluto unlike the classical planets. So now we have a whole body of objects that are similar. So even though the definition of what a dwarf planet is somewhat flawed, I'm not going to go into the details, again, offline, it's a subcategory of planet. Dwarf planet still has the word planet in it, right? Our star, our sun, is a dwarf star. We're still okay with that, right? I mean, yeah, we are. Or did anyone just suddenly realize that they're upset about that? Because you don't want it to be a giant star for a really long time. So we've got all these bodies here, down along the bottom here. You know, Quarwar, Sedna, Haumea, Makemake, Pluto, Eris, and additional bodies that have not yet been formally classified as dwarf planets: Orcus, Ixion, Varuna, 2002 AW 197, which is flows right off the tongue. So if you can accept that dwarf planets are just a subset of planets, then we can keep going and not worry about the elephant in the room. So the Pluto system. Pluto system turned out to be extremely interesting and complex. When we launched the spacecraft, we knew of one companion, Charon, sometimes pronounced Charon. As the New Horizons spacecraft was going out to meet Pluto, they discovered Hydra and Nix. Then they discovered Kerberos. Then they discovered Styx. And the team got really concerned because the idea was to pass close to Pluto and take lots of data of this world. But if we're discovering all these bodies orbiting it, are we going to hit something? It's calculated we would be doing, 32,000 miles an hour when we go past Pluto. If we hit something, that's pretty much game over. Even something the size of a small rock will destroy the spacecraft at that point. So this is a concern that we had. Now, I noted earlier Pluto had a companion, Charon. I didn't call it a moon, and technically it's not a moon. A moon orbits a primary body. The center point of the masses between Pluto and Charon is actually in space about 840 kilometers above the surface of Pluto. So Pluto and Charon orbit a common point right here. So essentially, they are a binary planet system. This has not been officially recognized yet by the IAU or anything, but it's something to keep in mind. So in the future, if this comes about, we have a binary planet system in our solar system, which we've never seen before. So there's Pluto, as you can see right here in the center. Whenever you look at through a telescope at Pluto, you will not see the arrow or the designation. Just in case you have that opportunity. Pluto is faint, as I mentioned. For comparison, these numbers here, 9.2 on the right here, down at the bottom, 13.5, 12.7, 13.8, 11.7 up top. These are what we call magnitude numbers, or brightness numbers. The larger the number, the fainter the object. So for example, the sun midday sun is minus 26 magnitude. Venus, if you get up in the early morning, just before dawn, you'll see Venus in the morning sky right now. It's about minus 4. The full moon is about minus 12. And the stars get dimmer and dimmer and dimmer, as do some of the planets. Like Mars is about, what is it, David, about first 0 magnitude right now? First magnitude right now? So if you see Mars in the evening sky, it's about first magnitude. And it's a log system. If you're out in a very dark area, say you're out in the middle of Wyoming at night, clear, your eyes, depending on how good or young they are, can see down to 6th or 7th magnitude. These are exceedingly faint stars. Even the 9.2 you can't see with the naked eye. Pluto ranks right down there in the 14th magnitude. It's faint. It's hard to see. And picking that out of the background is difficult. So, who can see Pluto here? No, I'm sorry. I meant to say there's a test during this. All right, you guys tell me if you vote on something or not. I'll point to something, you tell me yes or no. This star here, this star here, this star here, this star here, that one right there. That's the most yeses I've heard so far. How about this one here? That one? Okay, like that. Okay, it's between these two now. All right, this was taken with the Cassini spacecraft at Saturn when the New Horizons spacecraft flew past Pluto. There you go. You guys failed. Sorry, you'll have to do a makeup quiz now. So there'll be a chance to, for you guys to get your points back. From Earth, Pluto is small. You've seen images with the Hubble Space Telescope that are just fantastic. These beautiful galaxies, these panoramic nebulosity, these beautiful star clusters. That's because these objects, even in space, even though they look small, have an area around them that the Hubble gets all this photons from. Pluto is just a dot, a few dozen pixels across, maybe, that the Hubble can see. This is a Hubble image from the mid-90s. You run it through a deconvolution program, and you can get this. You can see shadow details on Pluto. You can see light and dark areas on Pluto. And if you take enough images like this and you put them together, you can see Pluto rotating, and these dark areas are not optical illusions, they're real because they return time and time again. In the 2010, after the last servicing mission to the Hubble, the Advanced Chemical Surveys did its thing. Got better resolution. We have some more color. You can see big bright area here coming around the limb. See dark area here down the bottom. You can see this modulation here circling around. We can see this detail, but you're not reading plutonium license plates with this. You're looking at like maybe a pixel is 300 miles across or so. So the best way we can go out there now at this point to get better images is to go visit the planet directly. The first proposal to go visit Pluto was done by the Pluto Underground, this group of folks over here on the lower left. And they proposed Pluto 350. And then they proposed Mariner Mark II, and then Pluto Fast Flyby, and so on and so forth. And there's a few more that are not on this slide that they have proposed. And either they got the funding briefly, and then it was pulled, or they didn't get the proposal through, or it was canceled. Something happened, and they didn't get to do their space program until Alan Stern, right here in the lower right, who is the gentleman here in the sunglasses, got New Horizons through the proposal process. It's a very rigorous, very grueling process to get through a NASA proposal period, and they got it. They got the funding, and they had a few years from that point to build their spacecraft and get it launched. Because to get to Pluto in a timely manner, we needed to use Jupiter gravity to give us an assist to get out there. I'll go over more of that in a moment. So this is the spacecraft here on the right. You can see a couple of folks at the Hopkins University Applied Physics Lab working on it. The size of the spacecraft is basically the size of a baby grand piano. Not that big. There are 7 science instruments aboard. This radio antenna right up here is one of the science instruments. It has 2 solid-state recorders that currently are full after the recent flyby. And it really made use of the miniaturization of technology over the decades since they first started proposing for a Pluto flyby to get everything packed into this tiny spacecraft. Jutting out from the side of it, this black cylinder object with fins on it is the RTG, the radioisotope thermoelectric generator. That is our heat source. That's our power source also. It keeps the spacecraft warm so things don't freeze out there, depth of space, and it's all where all the power comes from. And it's powered by plutonium. We had a certain requirement level we wanted for the spacecraft to have a level of plutonium, but they were not able to give us that as much as we had hoped. So we went out with a deficit of plutonium, but we're still running with plutonium on there. The power on the spacecraft will continue until the 2030s, mid-2030s, late 2030s, depending on how much power we use. At that point, we will not be able to keep the spacecraft warm enough for things to freeze up, and we won't be able to push a signal back to Earth that it'll be picked up. But after that, we will lose contact with the spacecraft. That will be it. But in the meantime, that's still 15 years away. We have a lot of work we can do with this thing. So I mentioned the instruments here: Rex, Ralph, Alice, LORRI, SWAP, PEP, and SDC. I just want to point out the SDC as being unique of the instrument, as it's the only student-designed and built instrument that's flying on a NASA spacecraft that far out in the solar system. And a number of the students that worked on this back in the early 2000s got their PhDs on the data that they collected using their instrument. So, you know, you kids, you can do it. Just saying. The group photo down here at the bottom is a student. It was all student-driven. The only quote-unquote adult, non-student, the gentleman on the far right here, it was just their advisor while they did everything else. So there's a little bit of trivia on the mission. In the upper right here, you can see the Mission Operations Center. When the Voyager spacecraft had visited all the other planets, Jupiter, Saturn, Uranus, Neptune, the post office issued a series of stamps commemorating all the planets. And it had a stamp for Pluto. And on the stamp it says, "Not yet explored." So we put the stamp on the side of our spacecraft. We had explored it. Clyde Tombaugh passed away before we launched New Horizons, so he never got to actually see what we've seen. But before we sent the spacecraft out, Alan Stern, who, if nothing else, is a master at public relations and getting the word out about everything, contacted the family and said, "Hey, we would like to have some of Clyde's ashes to send to Pluto." So bolted on the side of the spacecraft is a small container of Clyde Tombaugh's ashes. He's the first person to have gotten out there that far in the solar system. He's still going. So we launched January 19th, 2006, and we buzzed past the orbit of the moon in 9 hours. Remember, for the older folks in here, the Apollo astronauts took 3 days to get out there. Of course, they were stopping at the moon. We weren't. And it was 13 months later we got to Jupiter. So we were up until late last year, we were the fastest launched spacecraft ever. The Parker Solar Probe, which recently launched back in August, I think has a faster launch, but I have not yet been able to ascertain what the number is. Anyway, so we did Jupiter flyby in February 2007, and then we hit Pluto in 2015. We went streaming past Jupiter here, and we used the flyby of Jupiter as an exercise platform to practice a flyby. This is the only object we would fly past before Pluto, so we pretended this was Pluto and did a whole flyby regimen with the planning and the scheduling and pointing the instruments, taking information, taking images from this point on. And we got a lot of cool information that other spacecraft hadn't been able to get from our vantage point. Down here in the lower right, some of you might see, I don't know if that's working. No, it's not working. This is a GIF image here that should be running. The 10-image GIF image of this blurry thing at the top is actually a volcanic plume on the moon Io that's actually erupting as it's flying past. So getting to Pluto, you look through a telescope, you say, yeah, Pluto's right there. I can see it. But if you want to put a spacecraft there, there's a lot of calculations that go into it. It's very hard because Pluto's moving, you're moving, knowing exactly where the spacecraft is, knowing exactly how fast you're going, knowing where Pluto's going to be, calculating how long it takes to get out there, you got the speed you're traveling. There's a lot of uncertainty in getting a flying past an object. Even a close one like Jupiter or Saturn or even Venus, there's a lot of uncertainty. Pluto is just that much harder, so far away and so faint. Our nav team have put together a flyby plan right at the beginning of the mission that would put us in, if you imagine Pluto's here, where my fist is, tiny box right here, about 7,800 miles off the surface. The box is like 60 by 90 miles across. We're trying to aim for the midpoint of that box, okay? It's 3.1 billion miles away, and it's moving. They planned that out 9 years before we got there. We kept refining things over that 9 years, but this is what they did. Other things that we had to deal with were contingencies. What if something went wrong on the spacecraft? What if something went wrong with an instrument? What if something went wrong with the power? What if something went wrong with the computer? We had 9 years to practice contingency. And we had a team of very evil people that their job was to dream up problems and then send it to the relevant team members on the mission. And those members had to treat this as a real problem, just happened on the spacecraft. They need to resolve this right now. And then come back and present their resolution and what lessons they learned from it. So say they had a problem with the power. Suddenly we had a power drop. That could be one of the scenarios they dreamed up. The power people had to drop whatever work they were doing in real life and fix the scenario. And then present it to the team and mission managers and everyone else, say, this is what the scenario, this is what we did to resolve the issue. Very, very evil people coming up with these things. And they took inordinate glee at coming up with these scenarios. Another thing we have to worry about, I mentioned there's hazards. As we were getting closer to Pluto, we found all these other moons. So we had to start projecting different safe haven trajectories where if we see something that might be in this area, we can redirect the spacecraft. But we have to do it months ahead of time because moving this in space, we're traveling 32,000 miles an hour. We aren't going to suddenly do a 90-degree turn and go someplace else. We have to nudge the spacecraft at an angle to get onto a different trajectory. So they spent a long time looking ahead at the Pluto system to see if anything was there. So I mentioned the evil people and their schemes of scenarios to drive everyone crazy. Fix things. July 14th is our flyby. July 4th had a problem. The spacecraft went safe mode. Safe mode is a mode that the spacecraft is supposed to go into if there's a major problem on board and it can't resolve it with onboard AI. So it's called autonomy. Autonomy says, okay, if this happened, and I can't resolve it, and I have to pull power down the instrument, I have to bring everything to a lower state, then I have to go find Earth and talk to them and say, hey, I've got a problem. It's beyond my capabilities of fixing. Deal with it. And that's what we have to do. So July 4th, it was a weekend. I remember because I was in Western Maryland, out of cell phone contact. I had no idea this was going on. The flight ops team was in. They were doing a data transmission upload to the spacecraft while they were compressing some data. And this woman, the head of the flight ops team, Becca, was monitoring the telemetry stream. And periodically, it stays green most of the time, but periodically it will go gray when there's a telemetry dropout, but it'll come back up. So she was working on a document or something, I don't remember. And she saw the screen go gray. She goes, okay, I'll be back. So, and it's still gray. 30 seconds later, it's now time to panic. And because we have no telemetry space, anything could happen. We could have hit something. We don't know. So she starts making phone calls and sending emails out and texts out saying, got a problem, we lost telemetry, this is the time. One of the spacecraft engineers happened to be nearby, so he drove in when he got the text and asked, okay, what time did we lose telemetry? He told him, he said, okay, well, let's wait, I think it was like an hour and a half, and see if we get a signal. Meantime, we can't do anything except for everyone else to come in. Hour and a half later, they got their signal. Okay, the spacecraft's alive. We know that much. Don't know everything that happened. Now, everyone has to try to figure out, okay, what was going on with the spacecraft at that time, and what would have made it go into safe mode. The round-trip light time is like 9 hours to the spacecraft. You send a signal out, 4.5 hours to get out. What spacecraft's going to do whatever it does, that's going to take 4.5 hours to send a response back. Rebooting the computer is not fast on spacecraft. You can go home and power cycle your computer many times in the 9 hours it takes us to do one signal with the spacecraft. So basically what they did was once we knew we had a healthy spacecraft that was alive, we sent a signal that says, dump the telemetry so we can understand what was going on precisely versus theory crafting on the ground what might be going on. Meanwhile, while we're waiting for this round-trip light time, this RTLT of the signal to go out and come back, the team that was there started looking at, okay, we were doing this, let's start running the simulator and see what happened. And it turned out the main computer on the spacecraft got task overloaded, and it shut down. It was trying to compress data, which took longer than was anticipated. It was trying to process the next command load, which was coming in at that time, and it said, can't do it. I'm going to bed. We have two computers on the spacecraft. Second computer was basically a watchdog computer, and it was watching this, and it saw the first computer go belly up and said, okay, I'm taking over. I'm shutting the spacecraft down to safe mode. I'm going to point the antenna to Earth, and I'm going to say, help. And that's what it did. It did exactly what it was supposed to do. So it took us about 48 hours to get the spacecraft back online again, get the command load up and running. We were back in healthy, running 100% on July 6th. July 7th, we started the encounter sequence with Pluto. We lost a few images along the way, but they were not critical science data. They were opportunity images. So best case scenario of a worst case situation, and it turned out to be one of the scenarios that the evil team never got around to sending us. That was the only problem we've had so far to date, knock on wood. So this is the trajectory New Horizons took through the Pluto system. 740-ish or so, 730 to 40, I don't remember, is close approach. We zipped out, and then way out here to the far right, hours later, the spacecraft turned back to Earth, stopped taking science for 15 minutes, and sent a phone home signal. Because of the antennas fixed on the side of the spacecraft, it cannot point to Earth and communicate with Earth while it wants to do the science image, take data, because the camera wants to look up and down, side to side. So the spacecraft's constantly rotating and jogging about while we're doing the flyby. So during the flyby, it's completely on its own. The phone home signal came later that night. And all day long, we were on pins and needles. Though most of us denied it. Some of us said they were nervous. I was one of the deniers. That was like, I'm fine, it's cool. Yeah, we'll get the phone home signal. Until we got the signal, then it was like a big relief to the whole team, even me. It's like, okay, we do have a signal. We do have a healthy spacecraft. We are now going to start getting data now from Pluto. So a little bit of the stats on the flyby on New Horizons, launched in 2006, last Pluto 2015, traveled 3.1 billion miles to get there, 32,000 miles. Our target box is 60 by 90. We missed the center by 26 miles. Okay, that sucks. It's like shooting an arrow from New York to Los Angeles, hitting a statue in the eye, shooting a second arrow, hitting the statue in the eye, and missing by 1/4 of a millimeter of splitting that second arrow. Okay? We also arrived 88 seconds early. Okay? We had a 2-minute plus or minus on that center point. So we nailed it, basically. We were 7,800 miles over the surface of Pluto, and the best image resolution was 80 meters to a pixel, which is not too bad, all things considered. So these are some of the approach images as we're coming in. Up until June of 2015, the Hubble Space Telescope was seeing better images than we were able to with our small telescope on spacecraft. But by June, we were starting to do better than Hubble. And then on July 8th, we got to see Pluto. We got to see Pluto in detail. And you can see the bright region here that you may remember in some of the Hubble images turned out to be the heart-shaped region that is termed the Tombaugh ratio. As we approached over the days, Pluto rotated on its axis, so we got to see all parts of it. But the closest approach was over this hemisphere of Pluto. And this is an enhanced color image, but you can see there's differentiation in color on the planet. It's not all uniform color. The team gave informal names to a number of the features on Pluto. This way they could talk intelligently to each other about it, as opposed to saying the crater next to the double crater to the left of the crater above the 3-string crater next to the mountain by the edge of the glacier. Pardon? The Cthulhu ratio, yes. There's a Cthulhu ratio. There's a macula ratio. There's a crude ratio. There's a theme to all the names here. Okay. So these names were informal. The IAU came back later and ratified these names. These names are formal. So some of the names that were proposed by the team stuck. Some of them did not. Hillary Montes and Tenzing Montes were some of the names that stuck. And they hold a special place in my heart because I'm a rock climber and a mountaineer, and Hillary was Sir Edmund Hillary, and Tenzing was Tenzing Norgay, the Sherpa who went with him up and down Mount Everest. So this is the Sputnik Planum here. You can see there's a lot of weird modellated detail here, and then along the edges there's mountains and rough terrain. You can see nitrogen flows in basically the Sputnik Planum is a giant nitrogen glacier. But it's not a classical solid glacier. It's more bubbly like a lava lamp with these polygonal cells. Down here you can see rugged highlands and flat plains and pits. You can see some uplands here. You can see some of the cellular structure. You can see various icy hills that are forming, that are being carried around between the cells. You can see what appear to be snow dunes on these cells, and you can see some of the mountains here. The white on the mountains is methane snow. So for any downhill skiers, we have a place for you. Down here is the Hillary Montes and the Tenzing, the Tenzing or Norgay Montes. These mountains tower upwards of like 3 3/4 miles tall, some of them. Most of them are about the size of the Rockies out west, but some of them are taller. See this perspective view. They're very tall. And a friend of mine is currently working on a blog for a science fiction blog, if you will, proposing like a trip to Pluto to climb the mountains 200 years from now. He's writing it as if he's a mountaineer guy, and it's very cool. We also saw a couple cryovolcanoes. This depression right here is not an impact crater, but it's a volcano, but doesn't have lava coming out of it. It has nitrogen that splurts out of it when it forms. We didn't see it active when we flew past, but there's one there, and there's one just down off the edge of the screen. We also saw this frozen nitrogen lake in and amongst some of the lower mountain ranges. And this is a false color image highlighting some of the exposed water ice that we've seen that we can detect on Pluto. Pluto's bedrock is basically water ice, and it's covered with nitrogen ice and methane ice and other ices, so cold. And methane ice can be characteristic enough to cover the spectral response of water ice that we're seeing, especially over here on the left side, blue area. Craters. Pluto has craters, except in the Sputnik Planum, which tells us that most of Pluto's surface is very old. However, the Sputnik Planum is a very active region. It's constantly refreshing itself. So those polygonal cells that I point out, they're like a lava lamp. They're just bubbling up over millions of years. So if a crater forms there, it disappears after a few thousand or million years. It's gone. So Pluto is a very, very geologically diverse and interesting world. I'm going to run through a video here. It goes about 2 minutes that some folks have put together. It's like a flyby, if you will, over the surface of Pluto. So we're coming up from the bottom, going over the Cthulhu ratio. We're coming up to the mountain. We were 7,800 miles above surface. This flyby image using images that we got and stitched together as if you're flying somewhat close, like 100 miles, if you were 100 miles above. You see on the far right side, the Sputnik Planums over here. See some of the larger mountains popping up. You see the craters on the left. See the stars in the background. The surface of Pluto, if you were standing at noon on Pluto, it's as bright as being outside on Earth 5 minutes after sunset. So it's not super day bright, but you can see, your eyes adapt, you can still read stuff to it. Silence for everyone on the live. And you can see just the rugged terrain and everything around. So moving off from the terrain, the ground, Pluto has an atmosphere. How many of you guys knew Pluto had an atmosphere? 7 of you. Excellent. Pluto has an atmosphere. Surprise. It's a very, very, very rarefied atmosphere. It's like 100,000 times thinner than Earth's atmosphere. But it exists, and it's blue. It's a nitrogen haze atmosphere, and these layers that you see here above the surface are not JPEG artifacts. They're actual haze layers that we have seen in the atmosphere. And the atmosphere extends out. We've been able to detect out half a Pluto radius above the surface, which is really far, further out than Earth's atmosphere. Because we have an atmosphere, we have light scatter. We can use the light scatter to actually look at the dark side a little bit. So on the left here is a regular image that we took, and if you stretch it, you can see the light scatter, so you can see the post-twilight area of the surface of Pluto. So detecting the atmosphere, in the upper left here is how we were able to measure the atmosphere. We could, as we passed behind Pluto, we could see the sun's dimming slowly, slowly, slowly. Then suddenly it dropped off when we get behind Pluto itself, and then when we come back behind Pluto, suddenly brightens and then slowly brightens even more until we're outside the atmosphere. We also went behind Charon to see if it had an atmosphere. And you can see the brightness of the sun stayed until we went right behind Charon, disappeared, and then it came right back and then continued on. There's no atmosphere on Charon. Interestingly enough, though they're relatively close. There's a movie, it's basically a flyby movie. You can see these concentric rings here are the orbits of the other 4 moons. We pass over. Now we're going to go behind the sun, or behind the Pluto relative to the sun. You saw the atmosphere. Now we're going to do Charon, and it just blinks. And then we move out. Well, space is really dark, and we're really, really far away from the sun. So let's move off of Pluto real quick. We got still some ground to cover, and I don't know, what time is it anyhow? 10 o'clock, huh? All right. So Charon. Charon is this bump right here. that was discovered by this gentleman up here sitting down, Jim Christie. Astronomers prior to him kept seeing this bump, and they kept writing it off as instrument effect. But Jim saw it appear periodically, every 6 days or so, and change. He said, there's something real there. And they figured out that there's a body that's orbiting around Pluto. At that time, they thought it was orbiting Pluto, but we've since learned that's orbiting a spot between. Carrying on, this is the images from the spacecraft as we got closer, our closest approach image. The red area up here is called the Mordor macula. And all these names were unofficial, and this is where they derived from. So some of you who are culturally aware of these signatures. And these are the official names that were given. So Nemo kept his crater. Nasreddin kept his. Dorothy area over here. Argo. Kubrick bonds. Stanley Kubrick. And one of the things that we've been able to see, we looked at this this canyon feature here. Looking in, we can see these alluvial fans indicating landslides that have occurred on Charon. So it's also somewhat active. Not as active as Pluto, but there's activity on Charon also. And as we're departing, this is a backlit illumination of the backside of Charon by Pluto light. So hit the other moons real quick. Hydra. One of the first images we had of Hydra, once we got it down, we ran through a deconvolution program, and yeah. Okay. So Hydra's here. You can see it's a little bit lumpy, potato shaped with some holes. These are craters. Nix is over here. This is a slightly colored image. This color on Nix. Kerberos is over here, and Styx. This is the best image we have of Styx. It's small. It's like 9 miles across, and it was really far away relative to spacecraft those orbit. That's the best we've got of the tiny moon Styx. And for comparison to Charon, Charon's limb is down here at the bottom, and our other 4 moons. We also did some spectral studies of Nix and Hydra because we wanted to see what they were made of compared to Charon. So this spectral line here, white is pure ice, pure water ice. Nix pretty much mirrors it. There's some impurities on there, but it pretty much mirrors it. Hydra's close, Charon is less so. So there's water ice on Charon, but there's a lot more impurities on Charon than there are on Nix and Hydra. One of the current theories on how these formed is that sometime in the distant past, Pluto got smacked by someone. It probably spoke bad to its mom, and back then you were allowed to smack the kid. The teeth flew out, and now we're orbiting around Pluto. And that's what we have here, are these moons orbiting around Pluto. You can't smack your kid now, okay? Put him in detention, so we can't make more moons. So, we're leaving the Pluto system. We're moving on. The mandate of New Horizons was to explore Pluto and the Kuiper Belt. Should there be anything out there we can find? So we would be zooming through this region here, but while you see a lot of debris out here in this toroid, the distances between things is vast. It's tens to hundreds of millions of miles between objects, and many of them are small. We haven't even seen all of them. We've only seen a few thousand at this point scattered out there in space. And a few thousand scattered out there is really, really sparse. So Pluto is here, and our goal, which we found right about the time of the flyby, is Ultima Thule, which is right there along our trajectory. Along the way, we would be looking at other Kuiper Belt objects noted by these very imaginative numbered terms, as well as things, dwarf planets like War. Take images of those because we would get a different angle than we would on Earth, which is deep inside the solar system. So we could learn some tiny different things about it. But before we got to Ultima Thule or MU-69, we didn't even know it existed. We had to use the Hubble telescope to peer ahead of our trajectory path, find something out there we might be able to nudge the spacecraft forward. And if there's anything out there, we used ground-based telescopes. We saw nothing. There's nothing there. Ground-based telescope said, nope, blank sky. Hubble, after a while, saw this little dot move against the background stars. The background stars being the bright points, and the rest of this being noise in the CCD. As you can see, it's very, very close to the noise level. Hard to see. But you can see it moving against the noise in a regular straight line pattern. So we decided to go for it. We did some trajectory correction maneuvers, what we call TCMs, over the course of the years to retarget the spacecraft at Ultima Thule, MU-69. And the reason why we were doing multiples of these is because we just discovered this thing. The understanding of its orbit is very, very unknown, very imprecise. We have a very rough estimate of where it's going in its orbit. So over the 3 years, we just kept staring at this thing, kept data, the Hubble. Again, ground-based telescopes can't even look at this thing, but they can look at it not being, and I'll get to that in just a second. Ultima Thule, the name of it, was proposed by the team. There was a public call for, what do you want to call this new object we've come up with? And they got 34,000 names from the public, what to call it. It was pared down to 37, and finally decided that we will call it Ultima Thule. It's pronounced Ultima Thule, though you will hear people pronounce it Ultima Thule, Ultima Thule. Okay, fine, I'm not going to argue it. Ultima Thule basically means the furthest most northern land in ancient Greek and Roman. Now that we have visited it, a formal name will be applied by the IAU. They may keep it, or they may give it a new name. Don't know, but they will take our name into consideration. So I mentioned we can see it not being someplace in the sky. But by that I mean we can see it cross in front of the path of Ultima Thule, cross in front of another star and blink that star out momentarily. What we call an occultation. So there'll be a shadow path here on Earth where an asteroid will pass across a star, and so people who chase occultations will set a series of telescopes up perpendicular to that path and see who catches it, because the path could shift. They're not always exact, and who doesn't. And they can do a shape model of the object given the timing of each chord in that path. So you can see this on the lower right. You see where all these lines disappear and then reappear. You can get a rough potato-shaped model out of that if you draw the line around it. That's the shape of that object. These are timing. Where it disappears is how long it's disappeared for. So here it's disappeared for just a little bit. Here's disappeared for a longer period. Here it's disappeared for less long. So we had a few opportunities in 2017 and one opportunity in 2018. The Ultima Thule passed in front of another star. One of those opportunities was over the Pacific Ocean, so we had the Sophia aircraft, which carried a telescope on it, to go observe it. But the first opportunity was over South America, South Africa. They got nothing. They lined all their telescopes up, and nothing was detected, which was a refinement on where the orbit was not. So they knew they had miscalculated orbit a little bit. The second one here was where we sent the spacecraft over it, and it also didn't get anything. Third one was again over South America, the southern tip, and they got it. And then last August, we had another one that went through Colombia and Senegal. Colombia got weathered out. Senegal had 25 telescopes set up, and they got 3 hits. So you can see down in the lower left here, a star blinking out as Ultima Thule passes in front of it. And here is the chords that disappeared. So you can see it's got this rough, roundish, double roundish possible shape to it. This is what they inferred from the data, that it might be a bilobal object. It could be an elongated object. It could be a binary. We didn't know, but we would find out. Doing Ultima Thule is magnitudes more difficult than doing Pluto. Pluto was easy compared to doing Ultima Thule. And this is the laundry list of challenges that we had to address and overcome. having less power on the spacecraft than we did at Pluto. We couldn't do all the things we wanted to do necessarily. We had reduced budget for our resources. For Pluto, we had a full staff, 24 hours. Everyone was funded fully. Ignoring the government shutdown right now, we had a reduced budget, so people couldn't put as much time into the project as they might otherwise. We would be closer to Ultima Thule by a factor of 3 than we were to Pluto. We still had that tiny box to hit. We didn't know the orbit very well. We know the orbit of Ultima Thule even less than we do Pluto by a lot. We didn't know what hazards there might be in the area. Is this a swarm of objects and we just saw this one elongated or lumpy double ball shape or what? We didn't know. There's a lot of things we were very, very nervous about doing this flyby. Our approach time, we calculated, would be at 12:33 a.m. on January 1st, a few days ago. The round trip light time it takes to send a signal out, get back, is over 12 hours. So we wouldn't know for a long time anything that might happen. We're still traveling 32,000 miles an hour, and you could go from New York City to Los Angeles in 5 minutes, or you can get down to the Atlanta International in 6 seconds, as opposed to the half hour, 45 minutes it takes here. All right, the first images that we took were back in August. We downloaded them in September. We were, like I said, we'd be much closer, and this would be the most distant encounter with a body in spaceflight history. The anticipated resolution of the highest resolution images is here on the right. On the left here, the lower left, is the best Pluto image by comparison. So once we get the highest resolution data down, we should see incredible detail on this thing. With pixel being the size of a basketball. So I mentioned there's all these problems we have to contend with, and hazards. Again, hazards is a big deal. 32,000 miles an hour, the P in front of us, there's no more spacecraft. You can't see the P, unfortunately, because it's way too faint, but you can see if there's a larger rock that's maybe a few hundred meters in front of us. The team stared intently for weeks, looking ahead at our flight path, and determined there was nothing there. So we said, okay, we're good to go. We're going to go with the close-in trajectory. We had a backup alternate trajectory at 10,000 kilometers out if we saw any more debris in the area. Since we didn't, we were good to go with the close flyby. Instead of passing behind Ultima Thule like we did with Pluto and Charon, we would be passing pretty much directly overhead. And this is the timeline of events. These blue diamonds here are data downlink. We had 2 what we call fail-safe downlinks here. In case something happened at the flyby, we would at least have this data on the ground. Wouldn't be the great stuff, but we would have something. A little bit better than stick. It would be something. And then after the flyby, we had 3 more downlinks of data to go. And then we would go into solar conjunction, where we are now behind the sun. We'll be there for about 5 days. So there's Ultima Thule. This was taken in August. And the way we can see Ultima Thule is that the nav team that's using these optical navigation images takes multiple images. And then they overlay the images and subtract out all the things that don't move. And then we can see Ultima Thule itself. So in August, this is our first clear image of Ultima Thule. And in early December, same deal. The background is just littered with stars. And it's really hard to see Ultima Thule against like variable stars that are blinking and all the other stuff that's back there. Sometimes those pretty stars back. Just from perspective, this is the Earth, and come on, wrong way. This is Ultima Thule. This is the orbit of the International Space Station, orbit of Hubble. We would be that far off of Ultima Thule when we passed space. This is an artist rendition of Ultima Thule in the lower right, And this little dot here, how many of you are aware that NASA sent a mission to an asteroid called Bennu, and it went into orbit, like I think the 30th or 31st, around that. For those of you who don't know, NASA sent a spacecraft to this asteroid Bennu, and they went into orbit. It's a sample return mission. They're going to land a small lander on it, collect the samples, boost it off, and send it back to Earth for analysis, which is cool. But that's all the big, right? Our little guy is a few orders back large, but we're not doing the sample return on. So about a day before our closest approach, we got this image down, and we saw it's an oblong, possibly a bilobate shape. And we could see that it was rotating over a period of a few images, and that the rotation axis, we were coming in almost directly over the rotation, slightly oblate. So the lobe would be spinning like this. And then this is the image that we got down right after the closest approach from about half hour before the closest approach. And it turns out this is a contact binary. Two separate lobes that are connected. They're docked together. And they've been there for billions of years. And you clean that up a little bit, you get this image on the right. You can see the definitive bright areas. The belt right here is very bright. There's some darker areas. There's what appear to be depressions. We do not believe at this time they're impact craters, but the phase angle on this is like as you were staring at the full moon. You can't see the craters real well, but as we pass over it, we have images from different phase angles. We'll be able to see more shadow detail and determine, are these impact craters or this just a lumpy form and how it looks. We did get one set of color images down and we determined that it's a reddish color. And it's also pretty dark, very, very dark. It's like the darkness of potting. Okay? But we take long exposures, we can see these details. And the two lobes have similar color variations throughout, which says or suggests that they formed at the same time. So a theory is that there's a mass of debris that was forming at the very, very beginning of the solar system. It slowly accreted into these larger blobs. They spun around. There's a couple other little moons like out here. And then they basically docked. They came together at maybe a meter a second, or about walking speed. And if you were to take Ultima Thule and put it on Pluto's surface, that's all the large. All right, I just got a few more slides here, and then we'll do questions and stuff, because I know everyone's can't want to go to dinner or bed. I don't know. Who of you are familiar with Brian May of Queen? Who knew he's an astrophysicist? Yeah, cool, huh? He's been involved with the science team since Pluto, doing stereo imaging of Pluto and Charon stuff. He came again for the flyby. This was done on Monday, and I got a story to go with the image here on the right. We did a photo op with him after he took a tour of the Mission Operations Center, or our MOC, and we had a pass coming up to do a communication with the spacecraft. And so Becca here, just right of center, she's the head flight ops person, and she wanted to make sure everyone got their time in with Brian and got him through and got him out before she had to start working. And then suddenly she thought, wait, when we communicate with the DSN, the Deep Space Network, to set up the communication with spacecraft, we do a pre-task briefing. It's a small little paragraph telling the DSN, okay, we want kind of at this frequency, we want it at this elevation angle, we need this, we don't need to do that, we don't want you to do this. Just some laundry list of items that they need to be aware of. She said, why don't we have Brian May read it? And Brian goes, all right, in his British accent. He's very soft-spoken. And so we did a couple practice runs with him. So when he read it, he would be practiced to be able to read it smoothly like it's been doing it forever. So time came for us to do the track hookup. Becca did the voice check with DSN, read me, yes, got 5 4th. Okay, and then she announced the pre-pass brief will be read by Brian May. Said nothing more. 2 seconds later, Brian reads the pre-pass briefing very professionally, like he's been doing it all his life. Done. They terminate the connection, and we're all applauding and laughing. Okay, that was fun and all. And one of the guys says, I'll bet they're still processing what just happened. At that moment, the phone rang. Becca goes over, pushes the button, says, New Horizons Mock, you're on speakerphone. Was that real? I think it's one of the last images I have. This is an image that Brian May put together. For those of you who can do 3D viewing by crossing your eyes, this is what he does. I can't do it. I know Jason in the control room up there can do it, and he looked at it with his eyes crossed and said, it's cool. If you can cross your eyes, you can see a 3D image, more power to you. I can't do it. Got it. See if you got it. I got to see this through a stereo imager that Brian had, but he just put this on his website yesterday, so I can show it. All right, so some quick stats. We traveled 4 billion miles to get out here. We were still traveling at 32,000 miles an hour. The details of the offset on that tiny box that we had to hit are still to be determined. We don't have that data down yet, but we're pretty confident we nailed it yet again. We're just a little over 2,000 miles above the surface of Ultima Thule, so very close. Ultima Thule itself is 33 by 18 kilometers. It's bilobate. It's reddish. It's the building block of planets from when the solar system was first forming. This is building block. Where our planet at Ultima comes. What's next? We don't know yet. The door's open. We're still flying out. For the next 20 months, we're going to be downlinking the data from New Horizons. The data rates are really slow. For those of you who remember 200 baud modems, those are fast. For those of you who are younger and don't remember what a modem is, let's just say the bit rate's really, really slow, and you would get really impatient waiting for the web, because it would take days at this rate. So we'll be getting data down for about almost 2 years from the spacecraft. Meanwhile, we are going to start a campaign to look ahead, see what's out there. We have time before we get out of the Kuiper Belt. Kuiper Belt extends out to 50 AU or so, as we understand it. We're at 40 AU. We've got time to get through and see if there's anything out there using every resource at our disposal. Hubble, new optics on ground-based telescope, occultation experiments, and the LORRI telescope on New Horizons. We'll be looking, and if we find something and it's in our flight path, we're going to go for it. We'll have another flyby. Not, well, we'll just take ambient space information out there, take images of the other Kuiper Belt objects, and we'll report that. Thank you. All right, we got time for a few questions. Yes, sir. Yes. We transmit it through radio waves. Radio waves travel at the speed of light. All electromagnetic waves, X-rays, cosmic rays, gamma rays, light waves. It's the round trip light time is over 12 hours. One way is 6 hours. So we send a data packet out. It takes 6 hours to change to get out there. And if we tell the spacecraft to respond to us, it takes another 6 hours to piece. Yes.
If you can repeat the question, Mark.
Can
you repeat the question, please?
Oh, I'm sorry. First question was how do we communicate with the spacecraft? How long it takes and things. Second question was if the original team, the Pluto Underground, how many of them were there to see it? I don't know exactly how many people are still involved on it. I know a few are.
Okay, we have time for maybe one more question. One more.
In the back, dark shirt. Yes, sir. Did we find any what?
Any
New elements? We don't know yet. We don't have all the data down. Like, it's going to take 2 years to get everything down. So a lot of the spectra data is not yet down. So we don't know completely what this is made of. We got this one color spectrum image right now. But if you stay tuned on the website in the coming months, we aim to answer as many questions as we can.
All right, let's give it another hand. All right.